Step 1 in the hypothesis testing process is to define your hypothesis. A hypothesis is a statement about a population parameter that's subject to verification. So we could look at, for example, the average age of college students. And we want to know if the average age of college students is 19 or not 19. So what we would do is create a null hypothesis. Come on. And inside that hypothesis, we're looking at what is the population parameter. So here it is mu. We're looking at the average. And here we're saying the null hypothesis is that the average age is 19. And the alternative then is everything else, which is not 19. We could look at our hypothesis. Perhaps we're looking at the percentage of retirees in the northern US that sell their homes and move to warmer climates within 1 year of retirement. In which case we could look at, is the population proportion, so P, equal to 0.35, or the alternative, it is not equal to 0.35. Now we're going to talk about one-tailed tests and two-tailed tests. Two-tailed tests are where your alternative is not equal to, so it's quite possible the number is higher or the number is lower. But you can also have a one-tailed test where you are looking at, maybe you think that the proportion who move to warmer climates is actually pretty low, less than 35%, in which case the alternative here is a one-tailed test, and it just has one direction. We're looking at less than the number. The null hypothesis will always have the equality, and so here it's looking at the equals and the greater than. So we need to specify with our hypothesis what it is we are focusing on. What is the population parameter that we are testing? So a statistical hypothesis is a statement about one or more parameters of a population distribution that requires verification. Slightly different from a scientific hypothesis, which is a statement about nature that requires verification. With our statistical hypothesis, we're going to do that verification using that sampling distribution. Now, our statistical hypothesis must be mutually exclusive. So notice here that all possibilities are represented by the null and the alternative hypothesis, whether you have a one-tailed directional test or whether you have a two-tailed and you're allowing for it to be higher or lower. So if one is true, the other must be false if they are mutually exclusive. The null, this is important here, the null hypothesis is the one whose tenability is actually tested, whereas the alternative hypothesis is the one that's the researcher's hunch. So when you're trying to figure out what should be the null hypothesis and what should be the alternative hypothesis is always the one that you think is the case. The other thing to remember is that the null hypothesis always has the equality in it. So if the null hypothesis is equal, the alternative hypothesis is not equal. If the null hypothesis is greater than or equal to, then the alternative is less than. And if the null hypothesis is less than or equal to, the alternative is greater than. So you're really going to have one of those three scenarios. Now, in the examples we looked at just before, it was that we had a single population parameter, and we were then looking at it compared to a number. But you can also have your hypothesis be a comparison between two groups. So you could be looking at, for example, the difference between group 1 and group 2 in terms of their average and saying those two groups are the same versus those two groups are not the same. So your hypotheses can also include comparisons between different groups within the population. What we're going to be doing is we're going to be rejecting the null hypothesis or not rejecting the null hypothesis. So we never accept the null hypothesis, we only reject or do not reject. And that's because either the sample you're getting is so far away from the population parameter, that it must be different, that we can reject the null hypothesis, or it's close, but it's close because either it could be the same, or maybe your sample is not representative of the population, or maybe your methodology is not sensitive enough to detect the difference, or maybe your sample size is just too small. So we never actually accept the null hypothesis. We only reject it or fail to reject it. And that's because we don't actually know if it is the case that it is actually true, or whether there's something else happening, such as the sample size is too small or our test is not sensitive enough. So we're going to conduct hypothesis testing, where we're going to take our sample evidence and our sampling distribution, its probability distribution, and determine whether the hypothesis can be a reasonable statement. Can we attribute the difference between our sample statistic and the population parameter as just being due to sampling error, or is there actually a statistically significant difference? Okay, so when we do these hypothesis tests, we'll often use the word statistically significant difference, meaning that we reject the null hypothesis, that it can't just be due to sampling error, that what we think about the population parameter, that null hypothesis is not true. So how do we do hypothesis testing? First thing we do is state the null and alternative. Again, the alternative is what we actually care about. The null is technically what we are testing. So we write out the null and alternative hypothesis. So what would be the null and alternative in this example? Is the mean pulse of men over 50 years of age different from 90 beats per minute? Our population parameter is mu, and what we care about is that it's different. So the null hypothesis is equal to 90, and the alternative is not equal to 90. Remember, alternative is the one we care about. The null always includes the equal. How about this one? A public health worker implements a new exercise program to decrease the state's obesity rate. Before the program was implemented, approximately 40% of the sixth graders were obese. Did the new exercise program decrease the obesity rate? Okay. So here we're looking at proportions, and we could look at it in terms of a P1 and a P2, which is the obesity rate before and after. And so our null hypothesis could be that P1 minus P2 equals 0, no difference. And the alternative is that with the new program, that there is a difference. Alternatively, we could look at, if we're not comparing the results of the same people before and after, so that's a two-sample paired test, we could look at, is the proportion now equal to 40%? Our alternative here, we think that it worked. It decreased obesity, so we think that it's less than 0.4. Well, then that means the null hypothesis has to be greater than or equal. So more obese or the same number of obese. So it depends on how we've collected the data that we would build our hypothesis test. Here is the mean salary of college presidents less than 262,500. Remember, the alternative is the one we care about, so mu less than 262,500 versus mu greater than or equal to 262,500. Okay. So there's more here to try. Is the mean IQ score of 20-year-olds more than 100? Then null hypothesis then must be less than or equal to 100. Suppose we have a sample of individuals from the Arctic who claim to have a mean body temperature lower than what was generally understood to be normal. is the mean body temperature for all Arctic residents lower than that of the normal person? So we could do this as mu is less than 98.6, greater than or equal to 98.6. So there we're comparing it to a number if we're saying that is it more or less than 98.6. Alternatively, if you set this up as comparing one group from the Arctic and one group not, then you would actually be then comparing the average for one group to the average to another group to see if they were equal. Okay. So how are you setting it up that you're comparing it to a number or comparing it to another group? And there's a bunch more here you could try to specify the null and alternative hypothesis. So once we've specified the null and alternative hypothesis, the next step is to specify an acceptable level of risk. We call this the level of significance. This is our alpha. It's also called a type 1 error. This is going to be the probability of rejecting the null hypothesis even though it's true. So if we think about our sampling distribution here, let's say you want to be 95% confident, two-tailed test, 0.025 over here, 0.025 on this side. What we have here is that we are not 100% confident, we're only 95% confident. And there's a risk there that we might say that something is way out here, okay, so that it's not within what's reasonable, what's equivalent to the population parameter. So we would reject the null hypothesis, when in fact it should be considered to be close enough to be part of it. So you got to decide before the experiment, before your decision rule, before collecting your sample data, how much risk you're going to take. The smaller the risk, the larger the sample size you have to have. The greater the risk, the greater the probability that your results are wrong. Remember that alpha of 0.05 is what goes with a 95% confidence interval. 99% confidence interval is an alpha of 0.01. So the level of significance is going to help us determine the point at which the sample statistic is too far away from the hypothesized population parameter for the null hypothesis to be true. So remember we found Z alpha divided by 2, and those depend on that level of significance, how much risk that we're willing to take. So this is also called the type 1 error. If we're doing a one-tailed test, like what we see here, where we're looking at the null hypothesis being less than or equal to 10,000, and a one-tailed test that looks at that mu might be greater than 10,000, then all of alpha is in that one tail. That's why it's a one-tailed test, versus in a two-tailed test where we split the alpha into the two different tails. So it is the probability that we reject the null hypothesis even though it is true. So once we know what alpha is, once we know our significance level, then we can find our critical value. Our critical value being that Z or T. So here, what is that? Or in this case, is that Z alpha divided by 2. Those are going to be our critical values that are going to separate that dividing point between the region where the null hypothesis is rejected and the region where it is not rejected. Once we have these cutoffs between the region where the null hypothesis is rejected and the region that is not rejected, we have our critical values. We can then compare the critical value to what is called the test statistic. So the test statistic, I'll scroll back to this stuff in a minute. The test statistic is going to be the values that are based on the sample information. So our test statistic, we're going to take the sample data and do a calculation. So for example, for our t-test, we had the t-score, x bar minus mu, divided by the sample standard deviation divided by the square root of n. So we would do that calculation and get a test statistic, and we compare that number to the critical value t that was dependent on alpha, on that level of confidence, on that amount of error that you're willing to accept. So we compare the critical value and the test statistic. Alternatively, you can compare what is called a p-value and your alpha. So when we talk about, figure out where it is in the sucker, p-values. P-values are the probability of observing a sample value as extreme as or more extreme than the value observed, given that the null hypothesis is true. So when we get a test statistic, so we calculate that t-test, for example, from our sample data, then from there we can go to a t-table and find the probability in the same direction as alpha and compare it to our alpha. So if you end up with a p-value that is less than alpha, so maybe our alpha is 0.05 and we come up with a p-value that is 0.001, then we will reject the null hypothesis. Okay? If our p-value is greater than alpha, then we fail to reject the null hypothesis. And as we said a moment ago, maybe it's because the sample size is too small, maybe because our test isn't sensitive enough. There could be other reasons besides the fact that the null hypothesis is true. So in terms of the overall process, we came up with a null and alternative hypothesis. We determined the acceptable level of risk alpha. From there, we get our critical values that are based on that level of significance, that level of confidence, and then we compare that to the sample data by finding our test statistic, and we can either compare the test statistic and the critical value or the p-value and alpha. And then from there, what we'll be able to do then is decide whether to reject or not reject the null hypothesis and then make a final decision. So based on that, what does that mean? How do we interpret that? We're going to dive into all this in more detail in our next videos as we look at how to actually perform these different test hypotheses and coding them in Python or doing them in Excel. But before we leave this more general theory discussion, I do want to touch on a couple more pieces here. We talked about alpha as the type 1 error. So just go back here, type 1 error. But there are other types of errors besides type 1 error. So type 1 error, or alpha, is the probability of rejecting the null hypothesis when it is true. But we also have beta, which is the probability of not rejecting the null hypothesis when it is false. So we have alpha, type 1 error, and beta, type 2 error. So you make the correct decision if you don't reject the null hypothesis when the null hypothesis is true. And you make the correct decision if you reject the null hypothesis when the null hypothesis is false. We call it power, which refers to how powerful the tested is. How able is it to reject null hypotheses that are false? That is what we call power. And I just have a little definition, I think, down here. The probability of rejecting the null hypothesis when it is actually false, 1 minus beta. How powerful is the test? It determines whether or not the difference between sample statistic and the hypothesized parameter when there really is one. So can it detect power? Is that ability to detect the difference when there really is a difference? Well, power is related to beta. Beta is the probability that you don't reject the null hypothesis when you should have. So not rejecting the null hypothesis when it is false. And power is just 1 minus beta. Okay. We won't get into how to calculate type 2 error. You couldn't go into this detail in these formulas here. But the idea that we need to know and take away from this is the relationship between alpha and beta and power. So here we have our null hypothesis where we are assuming that this is our mean And our sampling distribution is capturing different X bars. And we're assuming that the average of the averages is that mean. So this here is our sampling distribution. Now, we talked about the level of significance, alpha, the amount of risk that you're willing to take. So the relationship here is that if we want to be, let's say, 95% confident, we go up to 99% confident, then our alpha is going down. But if we do that, so we move our critical value over here, then what we're doing is we're actually increasing beta. So when you decrease alpha and you say, okay, I want to be more confident, I'm going to accept less of the type 1 error, what you are doing is accepting more type 2 error. So if you're saying, you know what, I want it to be that I reject the null hypothesis when I shouldn't have. So when it was actually true, I rejected it. If I want less of that, where I falsely reject it, then what's going to happen is I am going to have more times where I did not reject when I should have. So when alpha goes down, beta goes up. There is this trade-off in terms of false positives and false negatives. We'll talk more about false positives and false negatives as we get into classification models. But so we can't just say, you know what, I want to be more confident without that confidence interval getting wider, without our test getting less sensitive. And so that then puts us into the other category, which is now we should have rejected things that we didn't. And so we're not detecting differences that we should have detected. So it pushed, you want to find the happy medium between alpha and beta when you're doing your methods. And that's why, you know, we tend to, when it comes to alpha, is we either do 0.01, so that'd be kind of like your 99% accuracy. We do a 0.05. If we have a very small sample size, then we would do an alpha of 0.0. We have a small sample size, we do our alpha of 0.1. Let's just get these in order here. So very small sample size, we recognize, you know what, okay, alpha is going to be higher, beta is going to be lower, but we're willing to take that risk because we just can't get a bigger sample size. Ideally, we want to have more 95% confidence interval, better balance between our alpha and beta. When we get into like medical testing and sciences, you want your alpha even smaller, 0.001. So we're not willing to have that alpha be high. And let's think about why. If we're doing a test and we are trying to see if a drug is effective, which is worse, a alpha or a beta? So alpha says we reject the null hypothesis when the null hypothesis is true. So this is saying the drug is effective when it's really not. Well, we're not willing to do that. So alphas are much lower in medical testing, whereas a beta, which says, okay, the drug didn't work, so it is but it actually did, we would rather have a higher amount of that. We'd rather have beta be higher in medical tests where there's that bigger risk if you're saying something is effective and it doesn't. You can't say this cures cancer and doesn't. So that's why in medical testing, we're doing 0.001 because we're willing to have a higher beta and a lower alpha. If we're talking about surveys, market research, we're talking about money but not lives, we really just can't get bigger sample sizes. We might be willing to do an alpha of 0.1, in which case the alpha is bigger and the beta is smaller. So there is this trade-off between alpha and beta, and there is a relationship to the power of the test. How powerful is the test at detecting a difference? So if you make alpha smaller, okay, then your test has to be more powerful to detect the difference. because you're not willing to have the error. So you need it to be a more powerful test in order to detect that true difference. So beta and power, here's beta, here's power. So when beta goes up, power goes down. Okay, so there is that trade-off between. And we know that when alpha goes down, beta goes up. So you can't see that because my head is covering it. But when alpha goes down, beta goes up, and the power goes down. Okay. So we got to be careful about the trade-offs between how strong do we need the test, how accurate are we willing to be. So just to clarify, because I think I misstated it earlier. Lower alpha, higher confidence, then you're going to need to detect more difference in that particular test.